Welcome to day 5 of the advent of compiler optimizations. We're continuing today on the theme of multiplication, which I promise you we're going to do some more complicated things than this, but it's great to get some fundamental understanding of the kind of things that compilers can do with the everyday stuff that we write in our code. Let's take a look at something in Compiler Explorer. Today, we're going to use the ARM instruction set to get a bit of variety and see how other architectures are handled by compilers. Over here, we're going to pick ARM, Clang, and I'm going to pick V8. There we go. And we'll pick the latest version of ARM Clang V8. So here we are. Let's do multiply and take int x, and then we're going to return x just to start with, just to show what an ARM no-op kind of routine looks like. And as we've discussed before, W0 and X0 are the first register that the ARM uses. So if you do nothing and return the value you were passed in, there's literally no work to do. So here it just returns because W0 already contains the first parameter, and that's kind of convenient. Let's move on to some of the other work. So we're going to do x times 2. And now we see that the ARM has a shift instruction, the LSL, which is a logical shift left. And it's just moving the W0 parameter up by one binary place, which doubles it. And no surprise, all of the other powers of 2 will be similar. So, we can do 32 up here, and we're going to see times 5, 64, and so on and so forth. So there's no LEA kind of instruction on ARM, but we have a shift, and we're going to use it for everything that is a power of 2. So let's try something that isn't a power of 2. Let's try 3. What happens? Here we see one of the cool tricks that the ARM architecture has. The ARM architecture has a barrel shifter, which is an arbitrary shift that can be applied to many of the operands of an instruction. So here we can see that it's using an add instruction to add W0 with itself, but the LSL #1 here means one of those W0s is shifted up by 1. So here we're taking W0 plus W0 times 2, which gives us times 3. And then similarly for other powers of 2 or adjacent to powers of 2. So let's try, something like 17. That's a power of 2 plus 1. We'll see that it's going to use the same trick here. What about things like 5? Again, 1 off of a power of 2, so we're going to use the add. 6. Now we're going to start seeing it using tricks like the x86 version we saw yesterday. That is, it's going to multiply by 3, and then it's going to double it by, in this instance, shifting it up by 1. Obviously, it could add it to itself too. I'm not sure quite why the compiler chose to do this, but that was what it did do. So again, we'll find that some of the more complicated versions, like adding multiplying by 25 or higher numbers, there is no cute trick now, and so the compiler has fallen back to using an actual multiply instruction. Those multiply instructions are typically a little bit more expensive than adds and shifts and things like that, so it tries to avoid them. ARM has a fixed size to its instructions, which means that there's only a limited amount of space to put a constant in. That constant can be shifted up a little bit as well, so that there's a bit of, it's not obvious which constants fit in single instructions, which don't. So if we try something like 1, 2, 3, 4, 5, 6 here, that constant value won't fit into a single instruction, and so the compiler has to build that constant by taking 5, 7, 9, 20, and then moving the top part with this movk instruction in, shifted up by 16. So it has to build that constant 1, 2, 3, 4, 5, 6 before it can multiply by it, which is kind of a surprise, and it's a quirk of ARM that is the case. I grew up with ARM v7, which is a much simpler instruction set architecture, only 32-bit, but it has some other tricks up its sleeve that we can't do in the 64-bit version. So let me quickly show you what I mean by that. If I select ARM v7 in here and pick this, we see first of all slightly different instructions. The instructions varied between v7 and v8. Here the constant's being built by taking this value and ORing in another value on top of it, which is effectively what that movk was doing before. But interestingly, we have a reverse subtract operation. Now, reverse subtract seems pointless. Why would you have a subtract operation that's kind of reversed, which lets us put the shiftable operand at the beginning of the subtraction? So that's the value that we're going to be subtracting from. So in this instance, what we're doing is we're taking R0, which is the input value, shifting it up 3 times, which multiplies it by 8, and then we're subtracting the original value of R0 from it. So it's the 8x minus x that gets us a multiplication by 7. So that's kind of cute too. Unfortunately, the reverse subtract seems to have been removed from ARM v8. So if we go back to our ARM v8 Clang 21, so here with ARM v8, you can see that it took 2 instructions to do the same thing, where we have to do the shift and then the subtract afterwards. Either way, the ARM instruction set has its own interesting quirks. That barrel shifter that can be applied to many operands is very valuable for a number of tricks, especially with multiplication and with array indexing, and mostly replaces the need for an LEA-like instruction on the ARM ISA. Tomorrow, we're going to move on from multiplication and addition and into something a little bit more interesting, maybe a little bit more interesting, division. See you then.